So what we're going to do in this one is we're going to take the camera and send it to the origin and line up the camera coordinate system with the world coordinate system. And then we're going to figure out top, bottom, left, and right. But we're going to do all of this for a perspective camera. So sending the camera to the origin and lining up the coordinate system uses the same M sub camera transformation that we did before for the orthographic camera. This is equation 7.4 on page 147. However, figuring out top, bottom, left, and right is a little bit different for a perspective camera, and that's what we'll spend most of the time on. So here's a perspective camera setup. What I have is the camera located at some position E, which is the I position, just as before. And then I have a gaze direction G, which is a vector. Both the I position and G are given in world space coordinates. And then I have T, which is a vector that points up and is in the same, and defines the plane along which the real F vector will be, kind of right about there. But for a perspective camera, I also have something different, which is called the viewing angle. In the textbook, the viewing angle is called theta. In my notes, I call it alpha, but in both cases, it's the viewing angle. So the matrix M sub cam takes the camera origin and the world origin, lines them up, and then lines up the camera coordinate system with the world coordinate system. And in these notes, I've assumed that you've already built the camera coordinate system using cross products. That process is described on page 147, just below figure 7.7. So at this point, what we want to do is look at the perspective camera in a side view. So the I position is now at the origin, because that's what the camera transformation did. And we're looking down the negative Z direction, and we're going to look at this vertically. So I'm looking at Y and negative Y. The gaze direction is straight down the negative Z-axis. That's what M sub cam did. But this time, instead of having a viewing rectangle like we had for the orthographic camera, we have a viewing frustrum or truncated pyramid because we're using perspective projection lines. So this angle right here is the viewing angle, which in the textbook is called theta, and in my notes is called alpha. Sorry about that. And what we want to do is we want to figure out where the top, the bottom, and the left and the right of this viewing volume is. The way we're going to do that is we're going to assume that all of this is done in terms of the viewing plane, and the distance between the eye and the viewing plane is given by the near field distance. So the absolute value of the near field distance is the distance between the eye and the viewing plane, and that's given by the absolute value of n, just in case n was negative. This is given to you by the user, so that's a given. So our objective then is to figure out where the top of this viewing volume is, where the viewing plane strikes the perspective lines that are the viewing angle. So what I want to do is figure out this distance right here, and I'll call that T for the top of the viewing plane. And then I want to figure out this distance right here, and I'll call that B for the bottom of the viewing plane. So what we've got here is we've got a right triangle that looks like this. This angle, this is the height we want to figure out. This is T for top, and then this is N, or the absolute value of N, which is the near field distance to the viewing plane, and then this is T, or the top of the viewing plane. This angle right here is theta over 2, because it's only half of the viewing angle, so it's the half of the viewing angle. So I know this, and I want to figure out this. Well, it turns out that the tangent of theta over 2 is T over N, so I have the tangent of theta over 2 is equal to T over the absolute value of N, because the tangent of an angle is the opposite edge divided by the adjacent edge. So that means that T is equal to N times the tangent of theta over 2. So now I've figured out where the top of the viewing plane is. The next thing I want to do is figure out where the bottom of the viewing plane is. Well, the bottom of the viewing plane is just in the opposite direction, same distance as the top of the viewing plane. Great. The final thing I want to be able to do is to figure out where the left and the right edge of the viewing planes are. To do this, I need to know the aspect ratio of the display device. So what I need to know is, am I looking at a rectangle or am I looking at a square? So I want to know the aspect ratio of my viewing volume. And the way that I figure out the aspect ratio of the viewing volume is I look at the number of pixels in X and the number of pixels in Y, and that gives me a ratio, nx over ny. And that ratio is proportional to or equal to the size of my viewing volume to the right and the size of my viewing volume to the top. So just to write that down over here, I have nx over ny is equal to r over t. I know nx, I know ny, I just figured out t, and so I solve for r. So then I get r is equal to t nx over ny, and now I know where the right edge of my viewing plane is. In this particular video, the right edge of the viewing plane kind of sticks straight out from the paper. Now along the way, I've made the assumption that my pixels are square. So I'll just encourage you to think about where the assumption that my pixels are square came in. And basically, just to give it away, I didn't have to multiply these by scalar because the distance in nx is 1 unit of nx is the same as 1 unit in ny, because the horizontal dimension of my pixel was the same as the vertical dimension of my pixel. So now we have figured out t, b, and right and left is just equal to negative right. So now I know where the edges of my